balancing redox reactions. So this should be reviewed from Chem 1A. If you were in my Chem 1A, these are the exact same slides I taught you, because this is in the course outline for Chem 1A. But we're going to go over it again here because it's very important here. So oil rig. This helps us to remember the definitions of oxidation and reduction. So oil stands for oxidation is an increase in, oxidation, okay, oxidation is loss of electrons. Oxidation is loss of electrons, and reduction is gain of electrons. That's what oil rig stands for. So that's in terms of electrons. We can also talk about oxidation and reduction in reference to an oxidation state. We just looked at how when hydrogen and oxygen react to form water, there's oxidation reduction that occurs, and yet we don't see a specific loss or gain of electrons, but we see the shifting of electron density. Assigning oxidation states helps us to understand which one's being oxidized and which one's being reduced. Here's an example of a redox reaction. We have calcium reacting with water to form calcium hydroxide and hydrogen. The calcium here, it's pretty easy to see what's going on with that, because here we had calcium atoms with a 0 charge, and over here we have calcium ions with a +2 charge. So in order for it to become positively charged, it had to have lost electrons, right? So oxidation is loss of electrons. The calcium is being oxidized. What's not as obvious is where the reduction is occurring, because here we have 2 hydrogen atoms bonded to an oxygen atom, and over here we have 2 hydrogen atoms. Here we have hydrogen and oxygen bonded to each other, and so what's going on? There's no charges to look at. We can assign oxidation states. Here, hydrogen has a +1, oxygen has a -2. Over here, the oxygen is still -2, so nothing happened with the oxygen. The hydrogen here is +1, nothing happened with that hydrogen, but over here we have some hydrogen with a 0 oxidation state. Its oxidation state went down. There was a reduction in the oxidation state, which is reduction. Okay. When we balance a redox reaction, we have to balance it for mass, meaning you have to have the same number of carbon or calcium or hydrogen atoms on each side of the arrow, but we also have to have the charge balance. And some of these equations you are just not going to be able to balance by inspection. You can get the masses to balance, but you're going to have a dickens of a time with the charges. And so we use a half reaction method. So we take the equation and we break it into 2 half reactions, one for the oxidation, one for the reduction. You balance them individually, and then you add them back together. So first, let's review oxidation states, because you may have forgotten this. This is a long list given in order of priority, and it actually makes it appear more complicated than it really is. So free elements have an oxidation state of 0. If you have an element by itself, it has 0 oxidation state. If you have a monatomic ion, the oxidation state is the same as the charge. So a fluoride ion has a -1 charge. Its oxidation state is -1. Like charges, the sum of oxidation states of all atoms in a compound is 0. So if overall there is no charge on the molecule, all the oxidation states have to add up to 0. So in sodium chloride overall has no charge. So all the oxidation states have to add up to 0. Sodium's +1, chlorine's -1, those add up to 0. Everything's good. if you have, well, see, this is just so dumb. States in oxidation states in a compound is 0, a neutral molecule is 0. That's the same thing, isn't it? Polyatomic ion. So something like nitrate. Oxygen and nitrogen covalently bonded to each other, but overall this has a -1 charge. So the oxidation states add up to the same as the charge. So here the nitrogen is going to be +5, the oxygen is going to be -2. We'll talk about why that is in a minute. There's 1 nitrogen and 3 oxygens, and so you add those oxidation states and you get -1. Oxidation states are not the same as ionic charges. Oxidation states are a tool that we have created to help us keep track of what's going on. But it is convenient, although also confusing, that the oxidation state is often the same as the charge, if there is one. Okay, so when we're looking at adding these things up, we're going to add them up just like we would add up ionic charges. In their compounds, metals have positive oxidation states. Well, I look at that statement, I'm like, well, duh, because what kind of charges do metals have when they form compounds? Positive. The charge and the oxidation state are going to be the same. So if they have positive charges, their oxidation states are going to be positive. This is the part that's very important. It's not, you can't get this from looking at ionic charges. So with the nonmetals in non-ionic bonds, where you don't have an oxide ion, you have oxygen in something, then how do you decide what the oxidation state is? So we've got this set of rules. And this goes in order of priority: fluorine, hydrogen, oxygen, something in group 7A, something in group 6A, something in group 5A. And so you look at your compound or whatever you're looking at. If it has fluorine in it, fluorine is first choice. So this is order of priority. The first one you come to gets its choice. So fluorine, if it was an ion, would be a -1, right? So in this compound, fluorine gets what it would like, gets its first choice, -1. Hydrogen, as an ion, is generally +1, right? So if hydrogen gets its choice, it's going to be +1. Oxygen is next. Oxygen is going to choose -2. That's the same as its ion charge if it was an ion. Group 7 elements form -1 ions. Group 6, -2. Group 5, -3. So this list is saying who gets what they want. And you have to go down the list. So the trick is, how do you remember the list? So any of my former students remember? Pho. So pho is a yummy noodle dish, right? P-H-O, pronounced pho. So what if we just get rid of part of the P? You could still say that, pho, right? So now we've got fluorine, hydrogen, oxygen, 765. Pho 765. Okay? So the half reaction method, assign oxidation states to the various atoms, identify what's being oxidized and reduced. So identifying what's oxidized and reduced is not absolutely necessary for balancing the half reaction. But we need some practice in this because it is important for electrochemistry. So we're going to go ahead and do that. Then break it into 2 half reactions, one for oxidation, one for reduction. Balance each of those with respect to mass. So balance by inspection all the letters. Balance everything besides hydrogen and oxygen. Leave those for the end. Balance oxygen after you've gotten everything else straightened out by adding water to whichever side you need. Balance hydrogen by adding hydrogen ions. We are balancing these in aqueous solution. there is water available, okay? And the first set of rules we're looking at is for balancing in acidic solution. There are also hydrogen ions present. Water often participates in these redox reactions. Next, we're going to balance each half reaction with respect to charge by adding electrons. So you need to look at the total charge on the left side and the right side and make them the same by adding electrons where appropriate. So you're going to add electrons to one side or the other. So you do that for both half reactions. Then you look at, well, this one has 5 electrons in it and this one has 2 electrons in it. I need those electron numbers to be the same. So we're going to multiply all the coefficients of the reactions to get the same number of electrons. Then when we add them back together, the electrons are going to cancel out. That's why they don't show up in the final balanced equation. And then you should always verify, double check that everything's okay. So that's quick going through the rules. Let's do some practicing here. So I've got a short list of the instructions over here to help us out. So we're going to balance this redox reaction. Aluminum plus copper ion forms aluminum ion plus copper. So if you look at that, by mass it's already balanced, right? There's 1 aluminum on each side, 1 copper on each side. What's the problem? What's the total charge on the left? +2. And what's the total charge on the right? +3. That means an electron went missing. I know they're very small and squirrely, but can they do that? No, they can't. Okay. So let's assign oxidation states. What's the oxidation state of aluminum solid? 0. It's an element. What's the oxidation state of copper 2 ion? +2. Same as its charge. How about aluminum ion? +3, same as its charge. And the copper? 0. So aluminum is going from 0 to +3. Its oxidation state's going up. Copper's going from +2 to 0. Its oxidation state is going down. Its oxidation state is being reduced. It is being reduced. So the copper's being reduced and the aluminum's being oxidized. So we're going to write 2 separate reactions, 2 separate equations, and it's helpful to keep the arrows lined up. So I'm just going to write the first one first. So aluminum solid going to aluminum ion. So I'm going to take my species here that's being oxidized, and I'm going to write that over here, and then the product over there. So aluminum can't be transformed into copper, so it's the aluminum and the aluminum ion that are together in that reaction. And then I've got the copper 2 ion being reduced to elemental copper. So I've got my 2 half reactions. Okay? I need to balance them with respect to mass. I look at this, well, 1 and 1. 1 and 1, that's done. Then we have to do the charge. So here I've got a total of 0 charge on the left side and +3 on the right side. The only thing I can do to fix this is adding electrons that have negative charges. So I've got a +3 over here, and I need that to be 0, so that means I need to add 3 electrons. So aluminum forms aluminum ion. Aluminum forms aluminum ion by losing 3 electrons. What the heck? There's 3 electrons just went missing. There they are. Down here I've got copper 2+ on this side and 0 on that side, so I have to add my electrons to the other side. So I'm going to have 2 electrons over here as reactants. So we said earlier that aluminum was being oxidized to form the aluminum ion. Oxidation is loss of electrons. we look at this half reaction and we see that the aluminum is losing electrons. Reduction is gain of electrons. Here, the copper ion is gaining 2 electrons as being reduced. So we've got the oxidation, half reaction, and the reduction. This is oxidation, and this is reduction. Any questions yet?
Just a quick one, just a brief overview. Because I forgot, whenever, like, let's say aluminum had a coefficient of 2 right there, and it carried over to the product side, will the charge still change, or will it still be 3? Will the charge still be 3, or will it be like 6 now because there's 2 aluminum?
If you have 2 aluminum ions, you have 2 that are each a positive 3 charge.
Okay, so it'll still be positive 3.
It'll still be positive 3.
Okay,
Mm-hmm.
okay.
So we want to be able to add these 2 equations together and not have any electrons showing, because the electrons that are lost by one thing are gained by another thing, and we don't end up with electrons being given off or taken in. So 3 and 2 are not going to cancel out. So we need to find the least common multiple, which would be 6. So I'm going to multiply the top equation by 2. So we're going to go times 2 on this one. So that's 2 aluminums, making 2 aluminum ions plus 6 electrons. And then this one I need to multiply by 3. So I've got 6 electrons there, 3 copper ions, and 3 copper atoms. Everybody okay with that? Now we're going to add these equations together. So we have set this up so that the electrons are going to cancel out. This equation is producing 6 electrons. This half reaction is using 6 electrons. So the electrons cancel out. So those cancel out. And then we're going to write down the other stuff. The exact order doesn't matter, but I usually just follow the same order that we started out with. So 2 aluminum atoms plus 3 copper ions. Oh, I've got to get the chart. What? Yeah. Copper ions are going to form 2 aluminum ions and 3 copper atoms. You've got, I'm going to verify 2 aluminums, 3 coppers, total of positive 6 charge on this side, total of positive 6 charge on that side. It doesn't have to be 0 on each side. It just needs to be the same. Any questions? Yeah.
Do you have for examples like something that's more complicated versus just individually, like for maybe something?
Yeah, we'll do more complicated ones.
Because this one's you can probably do in your head, but
Yeah, this one, if you just stopped and thought about it, you could balance this one without doing the half reactions. You could say, well, I need to change these numbers a little so that the charges are going to be okay. But this is a good one to start on. Okay, let's do this one. This is also a pretty simple one. Balance this one in acidic solution. So let's practice our oxidation states. What's the oxidation state of H plus? Plus 1. What's the oxidation state of chromium? 0. How about hydrogen? H2. 0. And chromium ion? Plus 2. So what's being oxidized? No, the chromium's being oxidized. Oxidation is an increase in oxidation state. Reduction is a reduction in oxidation state. You catch that? Reduction is a reduction in the oxidation state. That's not a coincidence. Here we're going from plus 1 to 0. That's reduction. The other one's oxidation. Okay, so now we're going to make 2 half reactions. So I'm just going to start with H plus because it's just sitting there at the beginning. And, you know, this is still pretty simple. What is the product that goes with the H plus? It's got to be the H2, right? H2. And then the other one is going to be chromium going to chromium ions. So there's my half reactions. This first one is the reduction, and the second one is the oxidation. Balance for mass. Is it balanced for mass? Well, the chromium one, the oxidation half reaction is, but this one isn't. Here I have one hydrogen and two hydrogens, and that can't happen. So I need two hydrogen ions on the left. So balance with respect to mass. Now we're going to balance for charge. Over here I've got a plus 2, and on the right side I've got 0. So I need to have plus 2 electrons here. And that goes along with it being a reduction. Reduction is gain of electrons. The hydrogen ion is gaining electrons, and that's why it's a reduction. And down here I've got chromium and chromium 2+. I need to make the charges the same by adding electrons, so I'm going to add 2 electrons over here. Yeah, you thought the first one was kind of simple. This one is just very simple. 2 electrons, 2 electrons. I don't even have to multiply. Those are going to cancel out when I add these two equations together. And I'm going to get 2H plus aqueous plus Cr solid, forming H2 gas plus Cr2+. The process is important, though. Any questions? Yeah.
Don't you have like neutralize the H ion?
Neutralizing the hydrogen ion comes about when we're balancing in basic solution. So we don't have to do that yet. Any other questions? Okay, now the cheat sheet on the right is gone. Balance the redox reaction in acidic solution. Well, let's assign oxidation states. What's the oxidation state for Fe2+? It's +2. MnO4 minus. Okay, there are 2 elements in there. So they each have their own oxidation state. There's 4 oxygens, and just like in an ionic compound where each of the ions has its own charge, each of the oxygens has its own oxidation state. They're all going to be the same, but they each have an oxidation state. So we've got manganese and we've got oxygen, and we're like, well, we know it has to add up to -1, but we don't know what the manganese is doing. So let's look at the oxygen. What would oxygen like to be? -2. So the oxygen is -2. Each of them is -2. So you got -2, -2, -2, -2, and 1 manganese. So what's the manganese got to be?
7.
+7. Don't be afraid of that high number. It's okay. No, it's not 5. +7 and -2 added together are 5. But I have 4 -2s. Okay, so that's why I did this. So -2, -2, -2, -2, that's -8, right? -8 and +7 together make -1. Okay, over here, what's the oxidation state? +3. And the manganese? +2. Okay, so what's being oxidized?
Iron.
Iron. Its oxidation state is increasing. What's being reduced? The manganese. What's happening with the oxygen? It looks like it disappeared. So, that would be a problem if you're trying to balance this one by inspection. Okay, so let's write our half reactions. So Fe 2 plus aqueous going to Fe 3 plus aqueous. And the other one, we've got permanganate ion going to manganese ion. So I got my half reactions, balanced with respect to mass. So the first one is balanced for mass, 1 iron and 1 iron. This one, though, manganese and manganese, that's cool, but I have 4 oxygens on one side and none on the other. We add water, because this is aqueous, right? There's plenty of water. So I'm going to add H2O, and to get 4 oxygens over there, I need 4 water molecules. So I balance the oxygen. Of course, I've created another problem because now I've got hydrogens in there, so I have to fix that. So I'm going to balance the hydrogens using H+. So over here I have 8 hydrogens, so I'm going to have 8 hydrogen ions on the left side. Yes?
Why would you put ions and not just hydrogen? How do you
That's a good question. Why hydrogen ions and not hydrogen molecules or atoms? Because this is an acidic solution. And so in an acidic solution, there's an excess of hydrogen ions and there's water, right? There is not necessarily hydrogen gas hanging around. Okay, so then we have to balance for charge, right? So this first one with the iron, we need to add 1 electron over here. That was our oxidation. Let's go ahead and label that. That's the oxidation half reaction. This is the reduction half reaction. And do your math carefully here. So over here I've got positive 2. Here I've got positive 8 and a negative 1. So I've got positive 7 over here. I need to get that down to positive 2. I need 5 electrons. And go in there and double check it. I mean, do the math on your calculator if you need to. There's no shame in that. So now what do we need to do? We need to multiply the top equation by 5 because we need the numbers of electrons to be equal. This one has 5 electrons. This one only has 1 electron. And we can fix that up by multiplying the top by 5. So 5 of those, creating 5 of these, and 5 electrons. Now we've got it set up so that the electrons are going to cancel out, and we're going to write down what's left. So we're going to get 5 Fe2 plus aqueous plus 8 hydrogen ions aqueous plus permanganate ion, and that's going to form 5 iron 3 ions and manganese 2 ion and 4 water molecules. And you should double check that it all adds up. Any questions? Yeah. Where I got this 5 electrons? No. Or this one? No. That one? Okay, so I added 5 electrons here because I want to make the charge, the total charge on the left of the arrow equal to the total charge on the right of the arrow. And I'm going to do that by adding electrons to one side. We're not going for 0, we're just going for the same. So on this side I have a total of positive 2 charge, and before I added those in I had 8 pluses from the hydrogen and I had a minus 1 from the permanganate. So I've got a total of plus 7 over here, and I need to make it plus 2. So adding 5 negative electrons. Any other questions? So that one would be a little harder to come up with this just by staring at that, right? Yeah. Okay, here's another one. Copper and nitrate ion making copper ion and nitrogen dioxide. What's the oxidation state of copper? 0. We've got nitrate ion, Fa765. Fluorine? No fluorine. Hydrogen? No hydrogen. Oxygen. What does oxygen want to be? -2. So oxygen gets to pick. It gets to pick -2. I have 3 oxygens. They are each -2. So that's a total of -6. Overall, with the including the nitrogen, the oxidation states have to add up to -1. Right? So I've got -6, the nitrogen must be +5, right? Because 5 minus 6 is -1. Over here, copper's +2. What do I do with this guy? Fa765. Oxygen gets to be -2 again. This time there's 2 oxygens, total of -4, and this is a neutral molecule. So the oxidation states have to add up to 0, so the nitrogen must be +4 here. So oxygen gets what it wants, -2. There are 2 oxygens, total of -4. This is a neutral molecule. So the oxidation states of the nitrogen and the 2 oxygens together have to add up to 0. Oxygens are each -2. That means that nitrogen takes up the difference, and he's +4. So looking at this, you can look at copper going to copper ion and say, oh, well, yeah, the copper's being oxidized. But without oxidation states, how do you know if it's the nitrogen being reduced or the oxygen being reduced? Kind of hard to tell. Oxidation states tell us it's the nitrogen that's being reduced. Okay, so our half reactions. Here's copper going to copper ion, and nitrate ion going to nitrogen dioxide. So this top one, that's our oxidation half reaction, and the bottom one's our reduction half reaction. Balance for mass first, 1 copper, 1 copper. That's nice. Down here, 1 nitrogen, 3 oxygens and 2 oxygens. Have to add water. Because you could go around and around with those 2 and you can't make them balance. It's not possible. So plus H2O. So now I've got 3 oxygens on the right, 3 oxygens on the left, but now I've introduced hydrogen. Acidic solution, we're going to balance that with H pluses. So I need 2 hydrogen ions over here. Everybody okay with that? See what I'm doing? Then we balance for charge. In the oxidation half reaction, I've got 0 on the left and I've got 2 positive on the right. To make those the same, I'm going to add 2 electrons over here. And that makes sense because oxidation is loss of electrons, and here we show the copper is losing electrons. Down here, guess what side I'm going to put the electrons on? The other side, yeah. You're always going to end up with an oxidation and a reduction. You'll have electrons on the product side for one and on the reactant side for the other. So I'm going to have my electrons over here, but I have to figure out how many. So on the right side, I have no charge. On the left side, I've got 2 plus from the hydrogens and a negative 1. So that's a total of positive 1, right? So I only need 1 electron. Balanced for charge. I want to add these two together and have the electrons cancel out. This half reaction is making 2 electrons. So this reaction needs to gain 2 electrons.
Can you repeat what you said one time about violating the 1 electron?
Yes. So let's write it out. So from this 2 hydrogens, right, that gives me positive 2 charge, right? And this is a negative 1 charge. So I'm going to add those. And this has to add up to what I've got going on over here, which is a big fat 0. And so I've got x. What's x? Minus 1. Right? So minus 1, 1 negatively charged electron. So to get the numbers of electrons to be equal, I have to multiply this the reduction reaction by 2. 2 electrons plus 4 hydrogens plus 2 nitrate ions. It's going to give me 2 NO2s and 2 waters. It is still balanced for charge and mass. I just doubled it. Now we can add these together and the electrons cancel out. So I'm going to have copper plus 4 hydrogen ions plus 2 nitrate ions, forming copper 2 plus 2 NO2 plus 2 H2O. Any questions? So in the green salt lab, where you have to balance the equation, this is what you need to do. Break it into 2 half reactions, get the electrons equal, add them back together. Okay, what if it's basic solution instead of acidic solution? There's not excess hydrogen ions around, so that's not realistic. We're going to balance it in the same way. We're going to pretend it's an acidic solution, and then we're going to add 1 step at the end. So we balance these other than hydrogen and oxygen. We're going to balance the oxygen with water, balance the hydrogen with hydrogen ion. Once we've got that done, this is a basic solution. That means there's hydroxide present. So what we're going to do is we're going to neutralize the hydrogen ions. However many hydrogen ions there are, we're going to add the same number of hydroxide ions. When you put a hydrogen ion and a hydroxide ion together, what do you get? A water. Okay, we're going to add the same number of hydroxides to both sides, so it's not going to mess up the charge balance or the mass balance. It's just going to convert the hydrogen ions into hydroxide ions in water. So let's do this one. This says in basic solution. So you got to pay attention to that. Okay, let's practice our oxidation states. Iodide ion, what's the oxidation state? -1. Okay, permanganate ion. We did this one earlier. So the oxygen's -2 because it gets to choose in this situation. And there's 4 of them, so that'd be -8. So the manganese has to be +7 so that all of that adds up to -1. Over here, I've got I2. What's its oxidation state? 0. And MnO2, well, the oxygen gets to be -2. And the permanganate has to be what? +4. What's being oxidized? The iodide. The iodide is going from -1 to 0. That's increasing. The manganese is being reduced from +7 to +4. The oxygen is not doing anything. So half reactions, we've got our I-, I- going to I2. And we've got our permanganate going to MnO2. I'm going to balance this first one with respect to mass. I've got 2 iodines and only 1 over there, so it needs to be 2 iodides. Down here, I've got 1 manganese on each side, but I've got 4 oxygens and only 2 oxygens. So I balance the oxygens by adding 2 water molecules over here. Now my oxygens are good. I balance the hydrogens by adding hydrogen ions. So 4 hydrogen ions. And now I'm going to get rid of the hydrogen ions, because this is a basic solution. I got 4 hydrogen ions, so I'm going to add 4 hydroxide ions on that side and 4 hydroxide ions on this side. Four hydroxide ions and 4 hydrogen ions become what? 4 water molecules. Now you could wait till the very end to simplify that. Is there anything else we could simplify right now? I've got 4 waters here and 2 waters there. I could just subtract 2 waters from each side, right? Bless you. So make it 2 there, and let me get rid of that. I'm going to move my 4 hydroxides over. So that was a lot of fiddling around. Let's make sure that it's balanced. I've got 4 hydrogens on this side and 4 hydrogens on that side. 1 manganese, 4 plus 2, 6 oxygens there. 2 plus 4, 6 oxygens there. So it's still balanced for mass. Now we have to fix it up with the electrons. So the top half reaction, I've got 2 minus on one side and 0 on the other, so I'm going to add 2 electrons over here. Now both sides are -2. Just needs to be balanced. Down here I've got -1, and over here I've got -4. So I could fix that by adding -3 to this side. 3 electrons. -3 and -1 is -4, and over here I've got -4. Any questions? Yeah.
Are you referring to the hydroxide, or the hydroxide versus the permanganate?
Well, I'm trying to balance the charge. So the permanganate has a -1 charge, the water doesn't have a charge. So before I stick these in here, a total charge on this side is -1. And the total charge on this side, this is neutral, and each of these is -1, so that's -4 on this side. We're not doing oxidation states here. We're just looking at overall charges on ions.
So you wouldn't look at the top equation, and I guess it works out either way, but recognize that from the left it was +7, and on the right it was +4. So there's 3 electrons, so you need to...
That might help you out, but sometimes you might have a 2 in front of this. You might have 2 of these and 2 of those, and so then you'd need 6 instead of 3. I'm sure there are shortcuts. I'm just going to follow this set of rules. But that is why it's 3, because this is going from +7 to +3. And how does it do that? It does that by gaining 3 electrons. Question?
Going back to the sign of oxidation state, diatomic atoms are always,
Pardon me?
diatomic atoms are always 0.
Yeah, a diatomic molecule like, Cl2, Br2, O2, those are elements, right? And so their oxidation state is going to be 0. So if you've got 2 oxygens and one wants to be -2, is the other one going to be okay with being +2? No. They're going to say, hey, we'll just both be 0. So anytime you have an element, it's 0. So here we've got the 3-2 thing going on again. So we'll multiply the bottom one by 2 so that we can get 6 and 4, 2, 2, and 8. I often screw up when I do that, so double check. So I'm multiplying by 2. Multiplied by 2, multiplied by 2, 2, and 2. Okay. And the top one, in order to get 2 electrons to be 6, I'm going to multiply by 3. So that'll be 6 electrons, 3 iodines, and 6 iodides. Add these together. Cancel out the electrons. And copy it down. So 6 iodide ions and 4 water molecules and 2 permanganate ions is going to produce 3 iodine molecules and 2 manganese dioxide molecules and 8 hydroxide ions. How many electrons are transferred in our overall reaction? 6. 3 for each of these manganese. Any questions? Let's do another one. Oxidation states. I've got chlorine and oxygen. This is the hypochlorite ion, overall -1 charge. Fe765. Go fluorine, hydrogen, oxygen. There we go. Oxygen gets to be -2. And chlorine's like, oh man, I wanted to be -1. Doesn't get to be -1. What does it get to be? +1. Is he happy about that? Probably not, but tough. +1 and -2 add up to -1. Here we've got CrOH4, overall -1 charge. So we have to look at the elements individually. We can do Fe765 here as well. So hydrogen gets to be what? +1. And oxygen gets to be -2. And chromium is going to have to make it up. So here we've got, in this hydroxide, a total of -1 for each hydroxide, right? And there's 4 of them. So 1, 2, 3, 4 hydroxides. They're each -1. And then we've got the chromium. Oops, that's not even under the chromium. We've got the chromium. We don't know what that is. And this all has to add up to -1. So what's the chromium? +3. It's not hard math. You just have to know what you're supposed to be thinking about. Okay? Over on the right side, here we've got CrO4 2 minus. Who gets to choose what they want? Oxygen. Oxygen is going to be -2. There are 4 oxygens. So from the oxygens, we have -8. Overall, we need -2. What's the chromium? +6. And the chloride ion? -1. What's being reduced? The chlorine. Chlorine's going from +1 to -1. That's a reduction in the oxidation state. What's being oxidized? Chromium. Chromium's going from +3 to +6. Oxygen is not doing anything. Hydrogen doesn't even show up over there. Hydrogen's not going to be doing anything either. Okay, so half reactions. ClO minus, I'm going to leave the states out, I'm tired. ClO minus going to Cl minus. CrOH4 minus going to CrO4 2 minus. This is a basic solution, balanced with respect to mass, chlorine and chlorine. There's an oxygen here, so we balance that by adding water on the other side. Then we balance the hydrogens by adding hydrogen ions. Then basic solution, how do we get rid of the hydrogen ions? Add 2 hydroxides to each side. So I got 2 OH minus there and 2 OH minus over here. It makes sense to me to simplify it here because it becomes bigger numbers if you let it go on. So these guys, 2 hydroxides and 2 hydrogen ions makes 2 water molecules. So I'm going to erase that and write 2 H2O. And then I'm going to notice that I have an H2O over here. So this is going to be 1 H2O on that side and none over there. The gap's a little awkward, so I'm going to move this over. 2 hydrogens on each side, 2 oxygens on each side, 1 chlorine. Let's look at the one on the bottom. 1 chromium, 1 chromium. 4 oxygens, 4 oxygens. Well, this is convenient so far. I need 4 hydrogens, though. So I'm going to add 4 hydrogen ions. And we'd be done there if it was acidic solution, but it's basic. You can't have hydrogen ions floating around. So I'm going to add 4 hydroxide ions to each side. Four hydrogen ions, 4 hydroxide ions. That's 4 water molecules, 4 H2O. This time there doesn't happen to be any H2Os over there to mess around with. Any questions? Okay, now we have to balance charges. If you should end up with something where it's already charge balanced, that means you screwed up. Because if it isn't imbalanced with charge, then it's not a redox reaction, right? We've got to have electrons somewhere. So total here is -1 on the left, -3 on the right. So I need 2 electrons over here. -2 and -1 gives me -3 and -3. Here I've got -4 and -1. Got a total of -5 on that side. I've got a total of -2 on this side. So I need to add -3. So I'm going to add 3 negative electrons. Everybody okay with that? We got the 3-2 thing going on again. So we're going to multiply to get the numbers of electrons to be equal. So 6 is the lowest I can do that, so I'm going to multiply this equation by 3. Gives me 6 times 3 times 3 times 3, and gives me 6. The bottom one I multiply by 2. I'm going to get 8, and 2, and 2, and 8, and 6. So I've got 6 electrons and 6 electrons. The electrons cancel out. And I can start writing this down. 3H2O plus 3ClO minus plus 8 hydroxide plus 2 chromium thing there, 3Cl minus, 6 hydroxides, 2 chromates, and 8 waters. Is that good? It's okay. What can we do to make that better? We can simplify some of the things that are the same on both sides. I've got 3 water molecules over here, and I've got 8 over there. So if I just subtract 3 from both sides, that'll make things a little cleaner. So I'm going to take the 3 from there, and I'm going to take 3 out of there, so that'll make that 5. And the other thing I have going on is hydroxides all over the place. I've got 8 hydroxides here and 6 here. So I could subtract 6 hydroxides from both sides. And that'll give me 2 hydroxides. Okay? Any questions?